Hi folks, so I have another lesson for you on reaction coordinate diagrams. So one of the ways to represent energy and the reaction and the energies involved in the reaction is using a reaction coordinate diagram. And we have an example here. In this case, I'll go through the parameters that we have already placed on the screen. We have y-axis, which represents the energy of the reaction. So energy, how much energy does the reactant have or product have? The x-axis is showing the progress of reaction. So going from reactant to product, you can think of it as a progression of the reaction. Okay, kind of like time, but just progress of reaction. So we have labeled the reactants, and if you see the height of the reactants is higher than the height of the products. In other words, the reactants initially have more energy, and when it converts into a product, you will see it has lower amount of energy. Great. So we have the reactant and product established. Okay. So I'm going to show you over here the reactant. This is a reactant here. Okay. And the product's right here, down here. Okay. So I've placed those dots so that so that you know where the reactant and product are. Now, when the reactant converts into a product, it doesn't go in a straight line from reactant to product, right? There is, as we said in the previous lesson, there is this energy bump or energy debt that it has to go over. So there is an energy requirement, which is the activation energy that is required to convert reaction from reactant to product. So in this case, how do we identify where the activation energy is? Well, first of all, let's look at the symbols that we have on the right hand side. We have E subscript A, forward. That is activation energy forward. So when the reaction is going from reactants to products, how much is the activation energy? How much energy does it need to go from reactant to the highest point on the energy scale, right? So in this diagram, the reactants are right here and right here, and then it will have to go this high to get to that point. And therefore, this height, this is the activation energy forward. Okay, so we have just identified for going forward, this is the amount of activation energy. The energy required to convert reactants into products, we have to provide at least this amount of energy to the reactants so that it can convert from reactants to products. So we have just identified where this is. Perfect. Okay. Now, if you recall from previous lessons, what is delta H? Delta H is the change in energy of the system. So when a system converts from reactants to products, what is the change in energy? And that would be labeled as the difference between the reactants and products. So I'll try to label it here with a different pen so that you can actually see the distinction between my activation energy. So right here to all the way down here, this is the delta H, right? And in this case, you see the reactants are higher up and the products are lower down. So delta H is going to have a negative value or a direction down, okay? The direction down, in other words, we are saying it's negative, right? Because the reactants had more energy and products had less. And therefore, the delta H is supposed to be negative or an arrow showing down, showing that the energy of the system was reduced when the reactants converted into products. Okay, so we have identified where the delta H is as well in the coordinate diagram. Now, going for the next one we have is the reverse activation energy. So reverse activation energy, in other words, you're trying to go from a product back to a reactant. So product is at this height here, and you're trying to go back to the reactant. How much energy do you need to go back to the reactant? You will need all the energy, and again, this line was a little bit on an angle. I'll redraw the line here, from here all the way to that height. You can see I'm trying to match to this height here. Okay, so that is the amount of activation energy for reverse, E-A-R-E-V. So activation energy reverse, that is the amount of energy we would need to go back from products to reactants, right? So if you want to convert reactants into products, you need the EA forward, which is the forward activation energy. That's the amount of energy you need. In this case, less the change in energy of the system is represented by delta H. In this case, it's going to be negative because this is an exothermic reaction. Let's label it as exothermic reaction. RxN is short for reaction. And so this is an exothermic reaction. Reactants had more energy, products had less. Therefore, delta H was negative. The transition state is where the dotted line is. This is the transition state here. Transition state. And at the peak of the transition state, so when the molecule is at the peak, the molecule is considered to be in a form of an activated complex. So it's in the transition phase between the reactant and the product, and it has a very high amount of energy, and it is very unstable at that point. So that is called the activated complex. All right, so those are all the components for the reaction coordinate diagram for an exothermic reaction. We have identified the activation energy forward. We have identified the activation energy reverse. We have also identified where the transition state is and the location of the activated complex. Writing it up here so that you have the terms activated complex. So again, if you don't know what any of these terms mean, please go into your search engines. You can search what these terms mean and make sure you understand what a transition state is in a chemical reaction and an activated complex is in a chemical reaction. Okay, going further down, we have over here activation energy reverse, and we are trying to figure out what would be a formula that we can use to calculate the reverse activation energy. Well, if you look at the diagram, right, the amount of energy you have for EA forward plus the delta H value, right? Those two energies combined, right? Think of it as we're looking at the absolute values for both. That will be equal to the total amount of energy required to go into activation energy reverse. That will be the amount of activation energy reverse if you take the activation energy forward plus the delta H value. Okay, now if you want to calculate the delta H value, that would be then equal to activation energy reversed minus activation energy forward. And when you take the difference of the two, you will get the value of delta H. I hope this lesson was useful to you. You understood the meaning of activation energy forward, activation energy reverse, the enthalpy change of a system, transition state, and activated complex. If you learned something from it, please like, hit subscribe, and look forward to new lessons coming up soon.